All right, I think we are going to get started now. Welcome. My name is David Gottfried. I'm the Deputy Director of the National Nanotechnology Coordinated Infrastructure Coordinating Office, the NNCI Coordinating Office. I want to welcome you to one of our monthly webinars, this time in the area of innovation and entrepreneurship. And before I introduce Andy Lingley to introduce today's speaker, just a couple of announcements. So you can, this will be the last monthly webinar for 2022. We'll get started again in 2023. But you can look at all of our past events either on the events page of the NNCI website or on our YouTube channel, which you can find by just doing a Google search for NNCI in YouTube. And we're usually the top listing there, and you can find us that way and view all of our past webinar recordings. Of course, you can ask questions of today's speaker, and you can do that using the Q&A box, and we'll get to those at the end of the webinar. And with that, I will turn off my mic and video and turn it over to Andy to introduce today's speaker.
Hello, everyone. My name is Andy Lingley. I manage the Montana microfabrication facility at Montana State University. And thanks to everyone for joining us today for the Innovation and Entrepreneurship webinar. Today's topic, transitioning from university to clean rooms to industrial prototyping, is really important to me for a couple of reasons. First, I've worked primarily at university fabs, but I did a small stint at a startup, and we went through the process of working with foundries, and I found it very valuable, and it's impacted about how I think about my work here at MSU. And more importantly, my opinion is that the technologies that we develop in our clean rooms will have a more meaningful impact if we can encourage more entrepreneurship and encourage researchers to think about how to transition to manufacturing as seamlessly as possible. So to that end, we invited Dr. Urteaga from Teledyne Scientific Company to lend us his insights. He received his MS and PhD degrees in electrical engineering from UC Santa Barbara, and he's now the director of Foundry Products and Services at TSC, and he manages the Advanced Device Development Group. He has an extensive publication record, primarily focused on the development of ultra-high-speed transistors in indium phosphide. And as he's responsible for TSC's Foundry offerings, and because he interfaces with external customers for clean room fabrication and prototyping services, we figured he was the perfect person to teach us about this topic. So we're thrilled to have him here, and I'll pass it off. Thanks.
Okay, excellent. Thank you, Andy, and thank you, David, for the introduction. Again, I'm happy to be giving this talk. I started out my work in a university fab, and I've now made it to industry, and so I think I have a good perspective. And somewhat of a unique perspective. And so I'll be focused specifically on giving an overview of our experience at Teledyne Scientific in transitioning semiconductor and MEMS technologies from university clean rooms into industrial and prototyping, production, and a commercial fab. So I'd like to highlight during this talk some common challenges in the process transfer, lessons learned, and best practices, and offer insight into past and requirements to higher volume manufacturing. So my caveat at the beginning is, the focus of Teledyne Scientific is sort of bridging that middle ground between prototyping or initial development at an academic facility, and then moving into industrial fab for more prototyping or low volume production. But within the Teledyne sort of ecosystem, we also do have paths for higher levels of production, higher volume manufacturing through Teledyne Microline and Teledyne DALSA. Teledyne DALSA is one of the largest pure play MEMS foundries in the world, and I'll give some examples of how they approach, or fairly quick examples of how they approach the project life cycle for going into high volume production. I would like to discuss, just very briefly, paths for strengthening connections between an academic and industrial fabs. I think this is a good audience to consider that. And, my one caveat is that I recognize that this is a very Teledyne-centric talk, focused on the work that we do here. May not reflect engagement models with other commercial foundries, so apologies for that. But I have tried to make it not too much of a Teledyne commercial. However, if you'll allow me at least a few slides and sort of showing a little bit about Teledyne and how Specifically, Teledyne Scientific fits into the overall sort of microfabrication business within Teledyne. At Teledyne Scientific, we're located in Thousand Oaks. We're primarily a 3.5 and MEMS fab, looking at sort of diversified R&D and early stage prototyping. Within Teledyne, though, there are, as I mentioned, larger fabs, those being Teledyne Dulce in Bromont, Canada, again, a very high volume production fab in the MEMS side, and Teledyne Microline in Edmonton, Alberta. So I'll talk about sort of all of these aspects of Teledyne briefly, but the focus is really going to be on the work that we do in Teledyne Scientific and the business model we have here for doing both our own advanced semiconductor development and working with external partners to develop their processes and products. So, you know, Teledyne Scientific has a fairly long history in semiconductor MEMS development. We're located in Thousand Oaks, California. We actually used to be part of Rockwell, so we were formerly Rockwell Science Center for many years, and were purchased by Teledyne about 15 or 16 years ago. Again, we're a high mix facility, really specializing in non-CMOS, 3.5 and MEMS technologies, and you know, have a fairly experienced engineering and operations staff that work in these areas of R&D and prototyping. So within the Teledyne, you know, Scientific fab, we do work in a few areas. One core area for us is government-sponsored R&D, working on programs for, say, DARPA or ONR, different government entities to develop high-risk leading-edge technologies. And then from that sort of initial seeding from government funding, we also want to develop our own technologies and put them to commercial outlets. And so within that, what we have developed is a number of integrated circuit processes that focus on sort of high performance in indium phosphide and gallium nitride material systems. We offer those as open foundry processes with process design kits, and also develop our own IC products in those technologies that we develop for both the commercial market and also for other Teledyne business units. We also, however, in our fab, and this is really the focus of this talk, support clean urban fabrication and prototyping services for external customers. There we provide access to our cleanroom tools with engineering support for process development and integration. And we found in recent years this has been a growing business area with, you know, dozens of commercial customers really looking at primarily, you know, non-silicon, non-CMOS technologies that they may want to move into a more manufacturing suitable environment. So again, just a few highlights of what we do specifically at Teledyne. We're a fairly small clean room, mid-size, 6,000 square feet of clean room space. We have dedicated operations staffs with technicians, tool owners, and support staff, as well as device engineering groups in both compound semiconductor and MEMS. Our work in our fab primarily focuses on 100mm diameters, but we do have the capability to run smaller size wafers, which can be important in emerging technologies, and also up to 6-inch wafers. I won't spend a lot of time on this next slide, which is showing our capabilities and processes, but overall, you know, we support a large range of lithography capability from 1X down to E-beam lithography with both I-line and DPV steppers. Obviously support metal and dielectric deposition etch. And I think for the, you know, interfacing with external customer side, importantly, we also do support some levels of metrology and also these services that can include mask and layout assembly and initial work with customers, DC and RF electrical test, and also just process or say device design support as well. So as I mentioned, you know, one of the core areas for us is this high-speed compound semiconductor technologies in indium phosphide and gallium nitride. These technologies tend to be very high performance, and because of that, they target, you know, fairly small markets. So high frequency, high performance markets like test and measurement, where there may be small volumes, high margins to entry, and high margins, hopefully, on the profit side as well. So that's kind of where these technologies are targeted. And because of this, you know, our run rates tend to be relatively small in the tens to hundreds of wafers. And, you know, maybe of interest to this, you know, to this group and, you know, overall, we can say that a lot of these technologies kind of started out as working at universities. Our indium phosphide HPT process was initially co-developed with UCSB and under a DARPA program, or a number of DARPA programs, probably about 15 or 20 years ago, right about the time I joined Teledyne, and then transitioned now into something that we offer as a commercial foundry service. More recently, we've done work with UCSB, Umesh Mishra's group, to transition elements of a GaN end polar process into the Teledyne cleanroom. So we have a good history here of taking technologies that were initially developed at a university cleanroom, maturing them, putting the manufacturing principles in place to make them viable foundry offerings. So, as I mentioned, the present markets for our technologies do tend to be fairly small and niche, so wafer volumes can be small. And as everyone knows, advanced semiconductor MEMS work does tend to be capital-intensive endeavors that really require a critical mass of both work and infrastructure to sustain the facilities and personnel. So one of the keys then, if you're kind of dealing in these smaller markets, is how do you keep your fab utilization and realization up? And we do that, as I mentioned, in two ways: by trying to offer open foundry access, so letting other entities design into our technologies through either dedicated or multi-project wafer runs. And then also, and this is where I'll start to focus on this aspect of it, performing these fabrication services, prototyping and trying to do low volume production for external customers. So, this is, again, what we're trying to do here is kind of fit into this middle area in this flow chart, where we might be taking concepts that were initially demonstrated and shown feasibility in a university fab and move them more into the industrial R&D environment to hopefully eventually get them a place where they could go into high volume industrial manufacturing fab. I think everyone knows that semiconductor development can be a long and expensive process as we go through initial concept all the way through final production. And, prototyping, we think, is really a critical initial step in trying to, get customer feedback and also trying to develop cost models moving forward. One thing we found is that there aren't a lot of options for companies in non-silicon semiconductor technologies to do sort of this middle ground development into an industrial R&D fab. Where you may want, say, more of a manufacturing environment that you can get in a university fab. We know a lot of times startup companies, will start doing fab at a university fab, but then for investor purposes and also for, first customer purposes, they really need to migrate into something with more controls, more of a manufacturing environment for prototypes than initially go to market. So that's kind of the niche that we're trying to fill at Teledyne. And I can give you some examples of prototypes we've done and of low volume production we've done for external customers. This includes 3.5 based high frequency HEMPs and varactors, power electronics in both GaN and silicon, GaN based micro LEDs and lasers, 3.5 based infrared detectors, thin film transistors, silicon photonics, acoustic wave RF filters that utilize MEMS technologies, and also MEMS processing. We do have extensive deep RIE capability in-house, as well as looking at aspects of heterogeneous integration of 3.5s and silicon. So very sort of long list of technologies we've looked at, both internally and again, working with external customers to try to bring these technologies up in our fabs. So we offer, a few different ways of this foundry / fabrication prototyping engagement that span a fairly large range. Some of it can be as simple as offering process module support, doing specific individual process steps, dep, etch, or litho on customer wafers, or returning samples after completion. Those tend to have fairly minimal engineering interaction. They can be generally fairly quickly turned around, and I think it's similar to processes that are sometimes offered within, university nanofabrication networks, where staff members will take wafers and run certain processes on them. In addition to that, we'll also do new process development. So process development where we're working to develop either a new process or improve an existing process for a customer. There we'll define a development plan and sort of end goals. Those would typically have a very high level of engineering engagement with regular updates on development status. And then I think of interest, again, to this audience would be the process transfer, where we have a customer who's demonstrated a process at another facility like a university cleanroom. We'll map that process flow to our tool set, define required short loop development for the process transfer. And that, again, generally involves a high engineering engagement in the initial process transfer, where we run the short loop experiments and also initial engineering and integration lots. And the hope is that decreases as the process matures and we move more towards pilot production. And so that's the end goal in many cases, is to get to this pilot production or low volume production. That sometimes happens and sometimes doesn't, depending on the success of projects. But the idea is we develop a frozen process flow that's completely transferred to our tool set, provide a path where we can, again, provide samples to customers. Our run rate, volumes that we can support in our fab are probably up in the hundreds of wafers per year range, not the thousands of wafers per year. But it would give us a path to then going to higher levels of integration through other foundry partners in the future. And in some cases, maybe those volumes are sufficient for a lot of new and emerging applications, at least in the initial years. So I'll go a little more into sort of the project flow or how we might take on work in this area, again, working with these external customers. So typically, we have some web presence or, presence where a lot of it we're finding now is sort of word of mouth, where we'll get approached by customers interested in starting projects in these areas. Generally, in the early stages, we'll have some introductory, calls where we kind of discuss top level project objectives and scope and do some analysis of our capabilities to make sure it matches a project that we're signing up for. I'd say that initially, typically we'll have sort of these early discussions before we get into the details, which would be, signing an NDA to discuss more project specifics and also pricing. At that point, we'd probably do a first pass project plan and provide some ROM estimates for NRE and production lots. So just some sort of back of the envelope estimates of what we think the project's going to cost and where we think we could get to if we're running at moderate volumes. One of the things that comes up often in the early stages of discussion, I'll talk about that a little more, is sort of, terms of, and conditions of sale, specifically around IP rights when working with, outside foundries. That's something you definitely want to be cognizant of. It's not the most exciting, engineering aspect of things, but it's something that can take a long time to get through. After sort of that initial project initiation, we'll do a more detailed project planning and mapping of a process. So if you have a process up and running at a university clean room, we want to see how that may map into our tool set, define where there may be some process development that's required through short loop development. And at that point, we'll generally be ready to go into some detail for a detailed SOW or statement of work, as well as a formal quotation for sort of short loop experiments and engineering lots, to which the customer would issue a process or a PO. As I said, almost all of the process development we do initially involves some amount of short loop process development, where we'll be executing those short loop experiments that we outline in the SOW. I'll talk more about that in a few slides and how we try to scope that. But in general, we'll run a short loop cycle, review data with the customer, and then define either declare success or think we can go on the next stage of process integration, or we'll go back and define the scope for further short loop development if required. The next step from there is obviously, where it really starts, the rubber really starts to hit the road, say, in the full process integration. We may initially run lot splits for materials and our process steps. We define the metrology that we'll be collecting in the statement of work that we work with the customer, and are on the hook essentially to delivering what we're measuring and what we're seeing during the initial process development with the customers. We would deliver engineering wafers to the customer for evaluation. We also have capability to do electrical tests at Teledyne, and we'll often test parts for the customer here and provide data on that. And based on those engineering lots, we want to define the scope and SOW for either further engineering lots or short loops based on results from that initial development. And so depending on the complexity of processes or how the development goes, there can be a number of cycles, going back and forth between this engineering and short loop process development before we get to a place where we might say, okay, now we have a frozen process flow. We really let the customer try to dictate, just because the run rates tend to be low and customers often have different requirements, where we are to define a pilot production or when we're ready to freeze a flow. At that point, we'll define what data needs to be collected and what reporting requirements may be needed for the product wafers, and obviously also deliver the product wafers to the customer. So I'll go into each of these sort of areas in a little more detail, try to provide some examples of what we've seen, working with these customers in the areas. And again, one of the things I think I'd like to point out is that, the non-technical considerations, which oftentimes kind of hold up the initial work. I think in general, we work with an engineering side and everyone gets excited about a project. And that enthusiasm to get started quickly is not always matched by the administrative side. I'm sure everyone in the audience who's at a university can relate to that. But so, there's things that need to get in place before we can start work. One is obviously the NDA. Trying to get that in place, can take a while depending on requirements. It's preferred in general to start with NDA from the Foundry as a starting template. At least in our case, that tends to move things through more quickly. A second consideration is intellectual property rights or IP rights. This becomes a large issue, obviously, when working with entrepreneurs who want to protect their IP, and also with us as a fab who wants to protect any existing IP that we have. So those are generally covered in the terms and conditions in sales, or the T's and C's as the contract people call it. And in general, the most common thing is we don't want any ownership of starting IP that you come into the project with, or a customer comes into the project with. And we wouldn't want I don't think there's any expectation typically on the Foundry side of owning any IP that the Foundry may have related to processes or modules that they have coming in. So where it gets, questions or where there's some negotiation, we find typically in sort of the IP format is what happens if we start to develop, IP in our fab through POs or through work being done with customers. So the preferred method, at least from our side on the Foundry side, is that the Foundry continues to own the process IP to be able to use it in our fab, but grant some sort of royalty-free license to the customer so that they could use the IP in their products and in other fabs if necessary. Again, this is negotiable and is something that, in our experience, really needs to be set up front and can take some time. So, getting that discussion in terms of reviewing terms and conditions, with the lawyers getting involved, I think is one of the key things to try to get a project kicked off quickly. I guess another question is, what if within bringing up a process in our Foundry, you need to, some of our existing IP becomes a critical part of that process. We're open to licensing that IP, but again, those are discussions that should be had up front. And a third aspect, which is important and I think could be overlooked in a lot of cases, is just export control. We do work at our facility that crosses, into the military regime, but we also do work that's done for commercial customers as well. And so, doing an export classification is important to protect both us and the customers so that there's no, inadvertent transfer of material or information, that may require an export license. I won't go into a lot of detail, but there's ITAR, which covers, specifically articles that are designed for defense and space applications. So typically not, things that we would develop under these Foundries engagements that we're discussing. More typically, work that's being done is covered by the Commerce Department, by the EAR. And this covers commercial or dual use license. Almost every, typically semiconductor technologies are covered under what's known as the Commerce Control List Category 3. Those are generally sort of called out in terms of capability. For instance, if I had a transistor that delivered a certain amount of output power over a certain frequency, it would fall into a certain category of the Commerce Department export regulations. So, working with the customers to classify what we're building is important. We do have an export group at Teledyne that we can call on with expertise in these areas. And it's really to just make sure that we understand, that you understand, if there's any need for export licenses to take any of these fabricated devices to non-US entities. So again, not the most fun or sexiest stuff in the world, certainly these non-technical considerations, but something that really needs to be spelled out upfront in our experience when engaging with external customers. So, the next step, kind of as I mentioned, is this process transfer, process mapping step. And I'd say, one thing that we found is, really don't expect a one-to-one transfer of processes. There's always differences. And so to that end, we really encourage an early engagement between the process engineers at our foundry and with the customer. One thing, in our experience, we'd like to do as much as possible is to leverage existing foundry process modules that we have. So, don't reinvent the wheel or the photoresist process, so to speak. If we have, processes that we think will work for the structure that you're trying to make, we strongly encourage the use of those existing modules. From the customer side, asking for the process specifications or controls and tolerances when available is very important. But it's also important to know, sometimes people give specs for their stepper, for their, etch, and it'll be, the best case scenario on the flattest wafer. So identifying, what the wafer requirements are, diameter, topology, flatness for achieving those specifications, is important in those early discussions so that you can make sure you have the necessary tolerances in the process design or process specifications. We think it's important, and the customer side, to really highlight the critical process modules, those modules or processes that really drive the device performance, and to quantify the requirements of those as much as possible. And, to that end, try to differentiate between, a nice to have feature of a process and what you think you must have to meet, say, a specific performance target. During this transfer and mapping phase, we'll often have scenarios where, okay, there's tools or modules that may not be available at the foundry. If not, can we use an alternative process? Or, can we bring up the module in our existing tool set? That's one option. Can an external vendor be brought in for the step? That's another option. And, in some cases, it may be that we need to continue to use an academic fab or an academic partner facility, especially in the early prototyping stages where they may have an established process to keep using. So maybe an example of that is, I tried to kind of keep names out of this, but say customer A was someone we worked with. They had a 10 mass process that was run actually in a few academic fabs. At the start of the engagement, the customer would provide a pretty detailed process flow with their tool sets and process travelers, and they'd work with us at Teledyne to try to map those processes into our tool step. Early on, I think we identified, say, 4 or 5 new process steps specifically related to new materials or etch processes that would be required. So we defined short loop development that would be required within Teledyne to develop those. At the same time, there are some process steps, specifically ion implant in this case, that we'd have to continue to outsource. We don't have that capability in-house at Teledyne. So in the case of this development, our initial development plan was to start short loop process development for those new process modules at Teledyne. While in parallel, we did start initial engineering or prototyping lots where we did some split fab of processing some steps in the university fabs where they already had the processes established. So this allowed us to get a little bit of a head start in sort of the process integration steps, while in parallel, developing the processes, the key process modules at Teledyne. It also allowed us then to compare, results from when we initially brought up those processes at Teledyne to sort of the full integration that was done using the existing fab tools. So, as I mentioned, the short loop process development tends to be, a very main part of, the process development cycle. I'd say one thing, I think most foundries, and particularly at Teledyne, were reluctant to quote foundry work cleanroom process development work on a develop to spec type level, i.e., we don't want to say we will develop a process that gives you these specific characteristics, say a semiconductor etch, like with a specific sidewall profile, uniformity, and mass selectivity, or an ohmic contact with a certain contact resistance for a fixed price. Like, give us this much and we'll develop this. There's just too much uncertainty in this development for us to commit to that, and it's not efficient. Ultimately, it would give the customer a quote that's very large because we have to bake in, a large amount of uncertainty into our cost estimates. So what we find, works the best for this type of development is to, define the short loop experiments, kind of define where we are at a starting point in our fab and where the customer is in their development. And then from that, have a very specific and detailed statement of work for the short loops we're going to run. That would have the inputs, number of wafers, what mask sets we're running, what process parameters we're varying, and what data we're collecting. And then what outputs we'll get from those short loop experiences, the short loop experiments, the inline metrology, the images, be them optical or SEM, and electrical measurements. And so that, covers us. I think as long as there's open engagement and dialogue, the customer can understand what steps we're taking, can comment on, how they would like to see maybe the development done. And then we can, basically execute those short loops, review the data at the end, determine if we have to go back and define another round of short loop experiments, or hopefully, reach a solution where we can identify what process controls and tracking we want to keep in place to kind of implement the proper controls as we move this into the prototyping or pilot production phase. So again, maybe another example, let's say customer B wants to reduce their ohmic contact resistance in a 3-5 process flow. We'd work to define a short loops SOW with lot splits for metal stack, anneal temperature, surface prep. The customer sends us test wafers for those short loops. We would obviously, generate the SOW and quote for that job. The customer provides us the wafers for the short loops. We'd cleave, run as pieces in this case. We'd execute the short loops, measure TLM patterns at Teledyne, provide the results to the customer. And then hopefully, select an ohmic process flow. In general, we would encourage, say, for a step like this, no matter how small the change, is to incorporate a lot split of some sort in our next engineering run to understand the impact of even small changes on the overall flow. So, I think generally, trying to use common sense and best practices when implementing any changes in the in an existing process flow. So, the next step is the process integration, sort of engineering lots, and there, no clean room process, particularly when we start to get to multiple processes, is ever as easy as straightforward as it seems. Every process flow, I think, as people on this call are probably familiar with, looks great in PowerPoint, and then you start to build it, and that's where the fun really starts. So, when we're working to transfer a process from a customer's fab, we really are counting on the customer input to identify the critical process steps and known integration challenges. So we encourage, either weekly or biweekly calls to discuss where we are in process development. Early on, our recommendation is really to run more staggered lots with fewer lot splits rather than having, a high number of lot splits within a fab. We're not really, typical lot sizes, I can say, for our fab are in sort of the 6 to 10 range. It's not a, a silicon facility where you might run 40 wafers and split, 5 wafers in each. So lot sizes tend to be small. And for that reason, we'd again recommend staggered lots with different variations as opposed to running a lot of splits within a single lot, just because it can be difficult to separate signal from noise when you have a lot of lot splits within a single lot. The key thing in the initial, process integration and development is really the scope of the inline metrology and data collection, what we're going to share with the customer to let what we see during the process and if what's being built is meeting your expectations. So from that end, there tends to be a middle ground. We'll have some customers who will request a lot of data collection, but during the engineering lot phase, this can be a fairly manual process, and so given that, it can also slow, the speed of a wafer running through the fab. So for example, if a customer tells us, we'd like you to measure, the metal thickness from an evaporation run on every wafer at 5 or 10 sites on a wafer, I think we'd strongly encourage them to, with some data probably that, we see good uniformity across wafers in our evaporator, we'd recommend you just, measure a single wafer or a few wafers from the run. So trying to find that middle ground where you can get the necessary information, but in a timely manner, I think is fairly critical. Early in trying to scope the process development and at least the process integration steps. Again, maybe another example of how process integration might work. We had a customer working on power device fabrication in our fab, going through a fairly large mask flow. Initial devices, we saw some unexpectedly high series resistance in some of the device contacts. The customer performed failure analysis using FIB/SEM cross sections, and we saw poor metal step coverage in the interlayer dielectrics. This was obviously a parameter that we hadn't spec'd well in the initial process development. So based on that, we defined some short loop experiments to develop a slow loop via profile, executed that and validated with FIB and SEM imaging that improved the profile of the metal step coverage, and then would implement that modified process flow in follow-up engineering lots. So typically, again, the engineering lots is one area where we'll see a lot of back and forth between sort of measurements of the customer, failure analysis, and also, the running of more short loop development as you find things in the process flow. In terms of, so the goal again is to try to eventually get to this, pilot production phase. And during the prototyping stage, we do try to work with the customers to define what requirements they need to transition to the frozen process. Because the volumes tend to be smaller, because customers may have unique requirements, we're really looking for them to drive what production controls they want, what data recording and reporting they may want, or what quality requirements they may have. We don't necessarily have some boiler standard plate parts or standards that we need you to accept or would want you to accept. We're looking for you to tell us, what you are, because obviously it can affect the price of the job in many cases. And so we do try to work with the customer to define that. I'd say one area that we should note is that, a lot of the times we're working with, materials where we don't have responsibility for the starting material or epitaxy in the devices that we're fabricating. This makes it hard when we get to pilot production to sign up for, say, wafer acceptance criteria. Specific to device performance. For our foundry processes, obviously, where we're responsible for speccing the epitaxy and sourcing that, we can sign up for specifications for transistors performance. But if we have a customer who's bringing us material and, we're running our fabrication process, we can't, guarantee the device performance if we don't, have visibility on the supply chain for the epitaxy or starting material. And so in those cases, the acceptance criteria really has to be sort of measurable output that we have in our fabrication process, and not necessarily the final device performance. One thing we've often seen, and this is more, I'd say, with established companies who've used us for some prototyping work than with startup companies who are probably more agile and don't have all these things in place, is there can be a disconnect between the engineering side who's doing initial development and quality supply chain departments within the organization. So I can say that there's been more than one instance where we've been working with an engineering side and have developed sort of a process, and on their side, they'll start to pull in their quality or supply chain because they want to put parts from this in their project, and maybe the first thing we'll get is a PO from the supply chain asking for so many parts of this part number that they've assigned to a process that we've run sort of at the wafer level a few times with the engineering department. So we kind of have to explain things, typically get everyone in the same room to work that out. And so our advice is to involve these teams early in the project if there is that infrastructure in place, and it needs to go through the quality and supply chains within the company. So I think in terms of other recommendations and best practices in this area, I think, at the university level, considering process compatibility early on with potential foundry partners in the device design can be really important. Unfortunately, I think one of the things that's lacking is visibility into what makes a process compatible, and hopefully, talks like this or more interactions with fabs like Teledyne and academic users can help, shed some light on that. But reaching out in the early prototyping stages to understand, or early development stages to understand, how you can make a process compatible both with sort of us at a smaller volume house or into a high volume house can be very important. I think taking advantage of Foundry e-test capabilities, electrical test capabilities, can be a very important part of the development cycle. We have standard probe cards, standard test structures that we're happy to share with Foundry partners. We can do auto probing here to provide, statistics and wafer mapping of key trends, of key parameters. So, leveraging that, particularly sort of at this initial startup stage, is important. A technical bugaboo that often, kind of hits people as they start to incorporate or move from a university cleanroom, particularly when they're working with, say, contact alignment, is, alignment marks when we're transitioning to a stepper lithography system. So the definition, placement, protection of the AMs, that becomes a fairly important part in the process development, particularly with certain steppers. And so, that's something we often advise early on is we have to consider, as boring as it is, just how you're going to keep your alignment marks in place and visible to the stepper as you go through your process flow. And I think, another critical aspect, and we found that the partners who have the most success tend to do this, is to start, failure analysis and device teardown very early on. We have, it's really critical tools for understanding what is being built. At Teledyne, we can do, sort of top-down SEM, top-down microscopy, but we don't have in-house fab capabilities. And so, we typically advise people to use external analytic companies for this. They have, reasonable prices. I would say in many cases, the picture is well worth the $1,000 you spend on it, or whatever it is for a cross section. So definitely encourage, the people who work with us to budget that in their development, and to plan for that by starting either additional wafers or test structures that can be sent for cross section and teardown. So some sort of frequently asked questions that we get as a fab doing this sort of work, and some answers. One of the most popular is, how can we get stuff out faster? It's particularly among startup companies who want to try to meet fairly aggressive schedules. And this is honestly a challenge in the prototyping, sort of early development stage. It's hard to guarantee a schedule when we're doing development, and it can run into a lot of issues. So the most often way, if a customer insists on us arranging this, is to, as part of our statement of work, we'll typically have an estimated schedule of some time. What we can offer in certain cases is essentially an expedite fee, where we say, okay, if we accelerate the schedule and finish in time that's, say, 25 or 30% faster, the customer pays us this much, additional money. That motivates us to try to finish the work faster. We can generally authorize, some overtime or additional work if necessary to try to meet those schedules. And it also covers the customer in the events where we may not be able to meet the schedules because something else happens. Another question we'll often get is, can we have a process engineer on site to kind of monitor and see what's going on? In our case now, that's a not generally answer. I would say no, but maybe there could be exceptions made. And this may be Foundry dependent. The big issue with us is that we found there's really too much overhead associated with us supporting the on-site visitors. Even though, it's somewhat the noisy wheel gets the grease. If you're on site, you tend to be in our site constantly. And so there just tends to be a lot of growth in the scope and interactions with those types of arrangements that it's difficult to budget for. So we can definitely support periodic site visits. I guess one thing we found was that COVID allowed us to more conveniently tell people that they couldn't come on site to sit on site. But moving forward, we're definitely prefer not to have process engineers on site here. Another, most typically people want to run stuff faster and also run it more cheaply. And so, we get, after we send quotes initially, a lot of questions about what can we do to reduce cost. In our view, engineering support is generally sort of the largest cost driver in the early development, and it tends to decrease as the process matures and it becomes more operator driven. So how do you decrease that early engineering support? We do think it's important and critical, but if there's process engineers on the customer side who can take some responsibility for metrology or data analysis, by either sending wafers back to get measured, or like I mentioned, sending things for external fib or SEM, then that can reduce costs, certainly in the early development side. So, that I think hopefully gave you a good flavor of sort of how we do things at Teledyne Scientific. Again, we were in the bottom corner of that box. I have a few slides now on how things work at the larger manufacturing houses within Teledyne Microline, and Teledyne DALSA. And those are, larger volume fabs, primarily focused on MEMS, operating at 150 millimeter or up to 200 millimeter in Bromont capabilities. So, they've, as they say, the transfer challenge there is how do you get from the prototypes into mass manufacturing, and when should you engage with these larger volume fabs? This is a slide specifically from DALSA/Microline, the MEMS side, about when's a good time to engage. So, too soon, your device design isn't set. Maybe you need to do advanced prototypes at a development fab. Market's not established. Customers guide the product specifications and pay for the product. Or if you don't have really a clear view of the manufacturing to ramp to volume. These large fabs really want to see your plan for ramping up to volume. But then the caveat is, obviously, you don't want to start and have to need wafers next month. So that's sort of, rough timeframes where they say, to get from sort of the initial initiation of a project out to the manufacturing gate, it's on this order of 2 years. I'll have some examples of work that we've done with DALSA that extended even, a little bit longer than that. So this is, I showed you our typical sort of work, or how we interface with customers. Obviously, at a large volume manufacturing facility, it's much more regimented and much more gated. This is an example of a typical project life cycle at DALSA, where you go through, many gates, initial proof of concept, followed by, 2 stages of prototyping, an alpha prototype phase, and then a beta prototype phase with specific, qualification roadmaps tied into each of those qualifications. That goes into pre-production and then eventually into mass production. So again, when we're dealing with the high volume fabs, a much more sort of regimented and specific infrastructure for scaling up to high volumes. Here's an example of some work that we've done with Teledyne DALSA transition, specifically a MEMS gyro resonator that we developed at Teledyne. This was a part that was initially done in a research fab, and it was actually moved to the Teledyne fab after about 2 years of development to optimize the process flow. We ran this for several years in small volume production, sort of 10 to 20 wafers per year. You can see in the picture there, there's about 16 devices total per wafer. We were, as part of a program, we transitioned this process to Teledyne DALSA's 8-inch fab that included wafer level vacuum packaging. And that was, a 2-year alpha lot development project. And then another 2 years of process optimization for device performance. So overall, that process now has the capability of running sort of thousands of wafers per year with 156 devices per wafer. So, almost an order of magnitude more devices per wafer with full wafer auto probing for known good die. Some lessons learned in this slide, which are very similar to lessons learned we saw, kind of working with us, is, knowing upfront the Foundry capabilities and where you should focus in the early demonstration. Process module development is important. I think there was, initial process, when we brought the process up here at Teledyne Scientific, it was before we were actually tied with DALSA. DALSA was purchased after Teledyne Scientific. And so had we known, the process modules available at DALSA, I think it would really inform the development we did in our fab to more streamline that transition into DALSA. Having good, accurate documentation of process modules is also important. And I think, as you move to these larger fab houses, the development can take longer than you expect. The initial low volume development may have lower priority in a production fab versus larger fab houses. And, process engineers to run development experiments at the larger fabs may also be limited. The last part, I'll just have a couple more slides left, but one item I did want to mention because it fell into this slide was another facility that's tied to DALSA. It's actually a public-private partnership in Bromont, close to the DALSA fab, called C2MI, where they do prototyping and low volume production work that specifically tries to tie to work being done at DALSA and also at IBM within Canada. So this is, again, is sort of a public-private research center in Bromont that tries to tie in industrial and academic development into next generation, either MEMS and advanced packaging. And one interesting thing about the C2MI fab is that they really have a link between sort of these academic or early users and finding a path into the DALSA fab. And that path is really tied by having common tool sets. So for example, if DALSA is interested in bringing up a new capability, they might first put it at C2MI and do the prototyping work there prior to pulling it into their large volume fabs. So it's sort of an interesting model. It's specifically a kind of a public-private partnership. And so I think an interesting question is, can you kind of follow that same route, or how do you tie better, academic fabs within the domestic US infrastructure to maybe industrial prototyping houses like, say, a Teledyne, or how can we strengthen those links that would facilitate the transfer of technologies from academic fabs through prototyping and high volume production. And a big aspect of that is I think tool manufacturers right now really focus on the high volume applications. It makes it difficult for people who are doing sort of lower volume prototyping to have the access to the tools that may be required to ease that transition. And so these are more sort of questions. It does seem that these challenges are being recognized more within the US government and DoD communities. And we're seeing, hopefully through things like the CHIPS Act and also the DoD Microelectronics Commons, maybe opportunities to tighten the bonds between prototyping centers and academia. So with that, I'll kind of wrap up there. Obviously there's a really strong base of academic microfabrication facilities that provide access to a lot of industrial users for early proof of concepts. But you can see that in a lot of instances, the commercialization of non-CMOS technologies, might not be well served within larger silicon foundries that tend to be established to address pretty specific and high volume markets. So we do think there's opportunities to work more closely with, users at academic facilities and for organizations like Teledyne to help transition, these non-CMOS technologies to the market. And a key there could be, again, trying to strengthen the connection between the academic and low volume manufacturing fabs. So thank you, everyone, for your attention and for joining today. Appreciate the chance to talk. I hope this gave you a good overview, and happy to take questions.
Thank you very much. That was really fascinating. And it looks like we've got several questions in the box already, and I've got another half an hour of questions myself. So I'll just try to run through them here. Derek asks, as a staff member at a university, we're often tasked with developing a process flow that, if successful, may end up at a foundry. What are the most important things that we can design in or out from the start to make university to foundry transition easier?
That's a good question. I think, I think it's somewhat dependent on the final end use, and so I think knowing where that where the end foundry is important. Obviously, if you're working on a technology that needs to go into a silicon fab, they're going to tell you, it can never have touched an ounce of gold, and it's it can't be in the same room as a gold pellet, essentially. Whereas if you're working with a Teledyne or a different foundry, there may be different requirements. So I think, understanding, in the early on, what the target to transition, what type of fab you're moving into is important. And then understanding the capabilities or process modules at those fabs is important. And I know that can be, difficult to have visibility on, but I think it's kind of an important step. So if you're able to, kind of visualize or have an idea where that next next step is in the process, then it helps you better answer that question essentially. So I'd say the more information you can get in terms of the end foundry state, the better you can design into the process, into a process that's acceptable for them.
Thank you. Okay, Ben asks, how well are the tools maintained for reproducibility? Are there backup tools if one goes down? And this sounds like it's specifically for Teledyne Scientific.
Yeah, so we do maintain tracking and control for most of our standard processes. Where it becomes somewhat tricky is if the customer design wants to develop a new process, or we need to develop a new process for a customer. Typically that is difficult to we would start the data collection of that step, and so we do have standard tracking, again, for these standard process modules that tells us the conditions of most of the tools that are being run or being maintained. And we can set up tracking as we bring up new processes within tool sets. In terms of having tool backup, I would say it depends. Certain tools do have backup, other tools may not.
Thank you. Okay, David asks, for optical MEMS and sensor applications, packaging can be rather unique. Is packaging within the scope of activity at Teledyne Scientific? What path forward for a typical customer with respect to packaging?
Yeah.
What paths forward exist?
Yeah, so we do some amounts of packaging, sort of wafer level packaging or MEMS type packaging within Teledyne Scientific. I think definitely within Teledyne DALSA, there's more work in that area and more expertise in that area. And so I think starting the discussion and finding out what capabilities we have here versus capabilities at either Microline and DALSA is definitely one that we can engage with to help in that area.
Okay, I think that's the last of the questions that I see that people posted in the Q&A. So my question for you is regarding guaranteed schedules. I was wondering, at Teledyne, do you keep data on sort of process complexity, maybe as a function of masks versus the timeline to make it through your projects? And do you use that data to help in the discussions on timelines when people are asking for things immediately?
Yeah, generally we have we have a fairly good idea of schedule or timelines per process step. So we'll generally try to map out a rough schedule for a customer early on, depending on the process complexity. So we'll have a sort of a standard turnaround time for a specific process step that'll help us take a customer's project and kind of outline a map. Now, within the development phase, a lot can happen, and so those tend to, those can tend to stretch out. But we will, in the early on, try to provide a fairly accurate schedule based on the process complexity in terms of when we can expect, say, a fab out of a given process.
Okay, and I've got another one for you. Are there any specific processes that you think university fabs should avoid if you're eventually going to end up at a foundry? This is sort of similar to Derek's question, but for example, at universities, we frequently use liftoff. And I was wondering if there are any things like that that maybe you'd say just don't touch if you're eventually going to go to a foundry.
Yeah, another good question, because I think liftoff is something that, if you want to go to a silicon fab, you want to avoid. However, a fab like Teledyne or a fab, many in the 3-5 realm, we don't consider liftoff a 4-letter word, so to speak. So we would allow that. I think, honestly, the big thing when we look at processes, where we tend to, I'm trying to figure out the best way to say it. If you have a process where you're counting on, a very small, when you run in the university clean room and only a very small portion of the wafer is working, right? Or, if say relying on on a lot of undercut, or stuff where you think, this requires, me to look under a microscope. I'm wet etching a wafer, and I'm, looking every 30 seconds to see how, pulling out to look every 30 seconds. That's hard for us to implement, right? So, understanding, etch selectivities, stopping, and things like that. Anything that, on your development side that's requiring a lot of manual interaction, for you to constantly inspect and go back for more, inspect and go back for more, I would say is not a good process for implementing in any sort of manufacturing environment. That's one of the big things we see. In terms of process modules, I guess I again would go to the who do you want to end up taking it to? If you do want to take it to a silicon fab, or if that's sort of the end goal, then having a liftoff, I would agree, isn't necessary. It is probably not to be done, but it depends who you're working with.
Okay, thank you very much. I was just looking at the Q&A and we got a couple more. I understand that we're now a tiny bit over time, but I'm very interested, so I'm going to keep asking questions.
I'm going to interrupt for just a second. So we are at the time, and folks do, I want to be cognizant of the time, but we can do, I can forward those questions directly to Miguel, and you can, with the person's email address, and feel free to reply to them directly. I just want to be, keep it within the hour if we can.
Yeah, thank you. Okay. Well, thank you very much.
Okay. Thank you, everyone. And thanks for the invitation to speak as well.
And thanks everybody for attending. And as I said, we'll see you in 2023 with our next NNCI webinar. Bye, everybody.
Thanks.